Yes, dear student, here is a question. The size of domain is 1 micrometer in case of Fe55, means mass is 55 atom mass. Density of iron 7.9 gram per centimeter cube. तो कहता है find number of atoms in one domain. I told you nearly 10 to the power 10 atoms are present. We will be verifying here. Maximum dipole moment and maximum anti-addition. Atom dipole moment of each atom is equal 9.27 10 to the power minus 24. If you remember, I have told this number earlier also. This is called Bohr magnetone. This is equal to Bohr magnetone. So here we will have to find out number of atoms in one domain. So number of atoms will be determined using Avogadro hypothesis and so many things. तो volume of domain हमारा a cube, size of domain 1 micrometer 10 to the power 6 meter 10 to the power minus 4 centimeter. Volume of domain 10 to the power minus 4 cube in 10 to the power minus 12 centimeter cube. So mass of Fe in one domain. Volume into density, volume इतना density ग्राम per centimeter cube. तो ये कितने 9.7 10 to the power minus 12 gram is the mass of iron in one domain. Atomic mass 55 gram. 55 gram of iron is equal to 1 mole of iron. 55 gram of Fe is equal to 1 mole. Means 6.023 10 to the power 23 atoms. So now how many atoms are present in this gram? Therefore, number of atoms in 7.9 10 to the power minus 12 gram. So 55 gram है, this 1 gram है, I take 6 10 to the power 23. Our idea is only there. Or into 7.9 10 to the power minus 12. It is the number of atoms present in one domain. If you roughly solve it, 6 into 9, 8 upon 55 10 to the power 11. 48 upon 55. 48 divided by 55. 0.0. 5 9 is 45. Nearly 0.9. 10 to the power 11. So nearly 0.9 into 10 to the power 11 or 9 into 10 to the power 10. Atoms of iron are present. Here exact number is 8.65. If you solve this by multiplying, it is 8.5. That does not matter here. My aim here is to tell you the method so that you may understand. So this is the number of atoms in one domain. The dipole moment of one atom is 9.27. So total dipole moment of one domain 9 into 10 to the power 11 or into 9.27 10 to the power minus 24 ampere meter square. If you solve this thing, it will come out nearly 8 into 10 to the power minus 13. 9 9 is 81. Yes. So it is 8 into 10 to the power minus 13 ampere meter square. Please note this number. It is the, what is this? Atomic dipole moment of one domain. So maximum magnetization What is intensity of magnetization or magnetization? Ka definition thi. Please learn the video. Make note from the video. Intensity of magnetization कह लो. Intensity of magnetization. Or simply magnetization. That capital M I told you is equal to magnitude M upon V. Net dipole moment per unit volume is the antenna. So dipole moment is this 8 into 10 to the power minus 13 और वॉल्यूम हमारा था 10 to the power minus actually 10 to the power 1 micron. 1 micron I told you 1 micron 10 to the power minus 6 तो cube 18 meter cube 10 to the power 18 meter cube. So if you solve this it will be 8 into 10 to the power how much 15. कुछ गड़बड़ होगा भाई. It is 10 to the power minus 13 upon 18 5 to bचा sorry 5 ampere per meter. So this way this is an idea how to solve the question. This is the question of NCERT book 5.11. 5.11 is the sole example. Actually, I have noticed we avoid NCERT, but NCERT book had model of questions. So please do this. Now I am taking another example again from NCERT book. This is important for every student who is appearing board exam or entrance exam of any NEET or any other engineering exam. There is one more good question here, and in my teaching experience I found this question is difficult for students. Here P is a bar magnet. Arrowhead shows direction of dipole moment of bar magnet. This magnet is named as P. It's pointing O. If a sold bar magnet is placed at point O, arrow with direction. Now there is another magnet Q. ये P है a Q position at Q1. Then it is here at Q2. The same magnet Q is placed first here, then here, or then it may be placed here also. If I take circle here. Centered at O, I can take like this. So here is another position of Q magnet, Q3. Here it is Q4, exactly opposite to this. Here it is Q4, Q5. Q5 is like this, on-right bisector, Q5, and then Q6. These are the Q1, Q2, Q3, Q4, Q5, Q6 are the position of another magnet Q placed in the neighborhood of bar magnet P. These are only two magnets P and Q. P is this, Q placed here first at Q1, then we may take Q2, then we can take it at Q3, Q4, Q5. So here you are asked in which configuration the system of two magnets will not be in equilibrium. In which configuration the system of two magnets will not be in stable equilibrium, and in which configuration it will be stable equilibrium, unstable equilibrium, and in which configuration the system of two magnets will have least potential energy. Least potential energy. I think I don't need to repeat the question again. First of all, you are asked in which configuration the system is not in equilibrium. I told you when a system of bodies will be in equilibrium. For any mechanical equilibrium, don't think of chemical equilibrium. Resultant of all force, all torque acting on body should be zero. What I told, for equilibrium condition, vector sum of torque zero, vector sum of force zero. Now if we think position Q, the mandible of P at Q1 will be perpendicular to Q1 because mandible line of bar magnet comes like this. कहीं भी जाएंगे यहाँ पर इन होगी. तो Q1 and P and mandible of this Q will be like this. So in situation Q1 and P and Q2 and P, the two magnets are placed perpendicular to the mandible of each other. So, and you know torque on bar magnet MB sin theta. Theta will be, this field is like this. So this is perpendicular to this. So maximum torque, यहाँ भी torque. So in configuration PQ1 and PQ2, the system is not in equilibrium. If there is resultant force, here resultant torque, resultant force is zero there. But resultant torque is there in this situation. So in situation PQ1 or PQ2, they are not in equilibrium. Now if I come to Q3, at Q3 field of this magnet and field of this magnet, so both the dipole moment इसका फील्ड B भी हुई है और मैग्नेट Q3 also parallel, तो torque zero. Here it is also the magnet field is this way, this Q6 parallel to this. Here magnet field opposite. तो torque equal to हमारा है ना MB sin theta. तो theta here zero, here zero. So equilibrium, and when I told you when M parallel to B there is stable equilibrium. So PQ3 and PQ6 they are in stable equilibrium. PQ3 and PQ6 stable equilibrium. यानी कि ये मैग्नेट यहाँ तो equilibrium, ये मैग्नेट यहाँ तो equilibrium. Now here it is anti-parallel. Theta 180. Equilibrium is there, but that is unstable. E unstable. PQ5, QP4. In position PQ5 or PQ4 will be in unstable equilibrium. Will be in unstable equilibrium. Now, in which configuration the system has least potential energy? So you know potential energy U बराबर minus MB cos theta. If theta is equal to 0 degree, वैसे भी I told you in stable equilibrium, the system is in lowest potential energy state. I have told you. So theta 0, then potential energy minimum. So here पैरेलल थीटा 0, यहाँ भी थीटा 0, तो दोनों में स्टेट इनमें भी in these two systems which correspond to least the potential energy depend also B also M तो फिक्स है दोनों का. तो here magnetic field on bisector क्या होता है, field due to bar magnet bisector mu 0 upon 4 pi और M upon R cube. ऑन तो बाइसेक्टर पर है, और एक्सिस पर क्या होता है, b इक्वल टू μ0/4 2m/r2. So in this situation they are in the field of each other. They are also in the, but here field is weaker than this. So if b get increased, so negative value increase, and therefore in configuration PQ6 system is in lowest potential state, lowest potential energy state. This is a very good question here, and we people keep on avoiding. Please don't avoid question. By doing question you get what we have learned. You revise your syllabus yourself. Now I will take other questions in next video. Thank you.